You buy the most expensive access point available, plug it in, and somehow your connection still drops 3 rooms away. The standard industry assumption suggests that increasing the transmit power on your hardware should equate to better range and reliability. In reality, maximum power often floods your space with wireless interference and drowns out the weak return signals from your devices. Building a reliable enterprise network is an exercise in physical geometry. Successful coverage depends on matching the specific shape of a radio frequency signal to the unique architectural layout of the space. This chart maps out the trade-off between hardware investment and engineering. On the bottom axis is the effort put into physical planning. The vertical axis shows network reliability. Low planning leads to overspending on equipment, while still leaving users with inconsistent connections and dead spots. High planning allows you to concentrate radio frequency energy exactly where the devices live, resulting in total stability with efficient hardware costs. Achieving true enterprise wireless requires moving past the maximum power myth to embrace deliberate network blueprinting. The baseline standard for indoor networking is the omnidirectional access point. A ceiling-mounted antenna pushes radio waves outward in a 360-degree pattern, creating a donut shape. Increasing gain stretches the pattern horizontally, but flattens it vertically into a pancake shape. This reaches further, but creates a dead zone directly beneath the device where users stand. For more complex spaces, you need the control of directional antennas, such as patch antennas, flat panel antennas, or sector types. Directional antennas focus the existing energy into a clearly defined boundary, much like a flashlight beam. This focus improves the signal-to-noise ratio in challenging environments like long corridors, warehouses, or outdoor patios. This physical hardware is distinct from beamforming, which is an adaptive software capability that helps equipment optimize connections to compatible devices. Beamforming can improve link quality, but it cannot fix an access point that is mounted in the wrong location or the wrong orientation. Controlling the physical boundary of a signal provides more predictable coverage than pushing omnidirectional energy through walls and floors. Beyond single-room coverage, you face the challenge of extending the network across sprawling campuses, remote buildings, or temporary event spaces. This flowchart guides network extension. First question, can you run a cable? If yes, wired backhaul is preferred for high-density, business-critical capacity. If pulling cable is impossible for a short-term agile deployment, you look toward wireless mesh. Mesh comes with a performance cost. Every wireless hop consumes airtime, which reduces capacity. To bridge long outdoor distances between permanent structures, a point-to-point wireless bridge is the most effective solution. A point-to-point bridge acts as an invisible wireless fiber cable, connecting two buildings without the cost of trenching physical lines. A common deployment error is assuming user phones and laptops can connect directly to that long-distance bridge. A bridge carries only backhaul traffic. You must install a separate local access point at the remote end for client devices. Prioritizing deployment convenience with mesh costs capacity, while prioritizing engineered bridges provides reliability at the cost of stricter planning. To finalize a blueprint, you must map these geometries and topologies to the specific requirements of your environment. We can group most networks into 3 primary environmental profiles. Each requires a different approach. In a standard office, you deploy multiple lower-power omnidirectional access points linked via wired backhaul to ensure predictable coverage through drywall. Warehouses require directional patch and panel antennas aimed precisely down aisles to bypass interference from metal racks and high ceilings. On a multi-site campus, you use point-to-point bridges for building-to-building links, which then feed traffic into local omnidirectional points at each site. Even with perfect access point placement, you can still fail by ignoring the final, most important physical constraint, the client device. Remember, Wi-Fi is a two-way connection. While an access point has immense transmit power, your mobile devices do not. An access point can shout its signal over a long distance, but a smartphone, a scanner, or a sensor must have the power to whisper back for a connection to actually work. A network must be designed around the weakest device using it. This is why a professional RF site survey is a non-negotiable step in the design process. Reliable enterprise Wi-Fi requires explicitly mapping RF shapes and networking topologies to the actual physical reality of the environment.